All right, for our last talk of the session, Neta will tell us about separating the wheat from the chaff.
Does it work?
Yeah, they're working on it. It takes them a minute. Okay.
Great. Okay, thanks. I'm Neta. Thank you for staying for my talk. So this is joint work with Adithya Murali and Shoham, my advisor. This is separating the wheat from the chaff, understanding incompleteness of proof mechanisms for separation logic with inductive definitions. Okay, so first, what is separation logic? And this is kind of a funny question to ask after this entire session, but maybe this is more for me to orient my first-order mind into separation logic. So separation logic is a logic for reasoning about shared resources and specifically locations in the heap in heap-manipulating programs. So we have some heap with two parts. One part of the heap, there's this formula psi that captures some property over it, and phi, and we can combine these joint parts of the heap with the separating conjunction, psi star phi. And in the way I think about it in this talk, so we have entailments that capture verification conditions. So we have this some verification condition that is captured by this entailment psi star phi entails alpha, and we ask, does every store and heap that satisfy psi star phi also satisfy alpha? And crucially, I'm going to talk about separation logic without magic wand. Okay. More specifically, separation logic with inductive definitions, SLID. So we enrich our language with inductively defined relations in the heap. So for example, we can have this inductively defined list predicate. So we can have a singleton list, which is just a nil, or we can extend some list from the left. So in this picture, we have the heap where D points to C, points to B, points to A, points to nil, and every memory location in the heap satisfies this list of X predicate. Okay, and SLID is a very expressive logic. We can do a lot with it, but it is incomplete. There's no complete proof mechanisms for it, and it means that when we try to prove things, we might fail, and we won't know exactly why we fail. But it does have some sound proof mechanisms. And one prominent one is fold-and-fold reasoning, where we reason by either taking an inductively defined predicate and unfolding it to its definition, or we take formulas that satisfy the definition of a predicate and fold them into applications of the predicate. And usually we expand and extend fold-and-fold with more reasoning, like inductive lemmas and stuff like that, but also by itself it can prove some entailments, but it fails to prove other entailments. And in this work we try to understand why and when that happens. So what is exactly the power of reasoning we can do with fold-and-fold? So let's begin with a concrete running example. We have this inductively defined acyclic list segment, lseg xy. So lseg xy holds when we have a singleton segment, x equals to y, or we have some segment lseg uy, and x points to u, and so we extend the segment from the left. And we ensure that x is different than y to have an acyclic segment. And this inductive definition gives us the following proof rules with fold-and-fold. So for fold, we have these two rules. So t equals 1, t1 equals t2. We can deduce lsec t1, t2. And for the other part, if t1 is distinct from t2 and points to some t3, where lsec t3, t2, we can also deduce t1, t2. And conversely, if we know lsec t1, t2, we can deduce the definition of the inductive predicate. Okay? And when we use this unfold rule, we introduce some fresh constant that replaces the existential quantifier from the definition. So let's take a look at two valid entailments that we would like to prove with fold and fold. So the first entailment, which is shown in green, which is good, says that A is distinct than C, and A points to B, and L-seg BC entails L-seg AC. So basically it says a list segment can be extended from the left, and this is provable with a single application of fold proof rule. And the second entailment that we want to prove is this entailment that says L-seg AC star C points to B star B points to nil entails L-seg AB star B points to nil, which is basically saying a list segment can be also extended from the right. And this entailment is true in separation logic. It is valid, but it's not provable by any amount of fold and fold reasoning. So no matter how hard we try, using only fold and fold, we can prove this entailment. And one way maybe to understand it is that the syntactic shape of the L-seg definition also only allows reasoning from the left side. Another way to say the same thing is maybe that any application of fold and fold proof rules on this entailment will never produce something with the shape of A points to T and L-seg TB. But I think that you all agree that these two explanations aren't very satisfying. So it's not really clear why we can't prove this, right? And we really want to know, like, the point of this paper is to understand why we can't prove this entailment with fold and fold, and more general, and for other entailments, can we identify those entailments that are not provable using fold and fold? Okay. So the high-level abstract answer is that fold and fold reasoning captures weaker semantics than separation logic, right? And weaker semantics means more models. So when we think of the entailment, we think of the set or the class of models of separation logic, and if for every model in that class the entailment holds, then the entailment is valid, but fold and fold considers more models. So there exist rogue counter models, so models considered by fold and fold reasoning that are not true separation logic models, and in those models, they violate this entailment. So they're not considered by, and they violate the entailment. So that's the high-level answer, and for the rest of the talk, I'm going to give a bit more concrete answers. So I'm going to introduce weak separation logic, which says weaker semantics for separation logic. And crucially, fold and fold is sound for that logic. So fold and fold reasoning must consider all of the models considered by weak separation logic. Then I'm going to talk a little bit about rogue models of weak separation logic, how to find them automatically, and also I'm going to answer this question, do they capture all failures of fold and fold? So do all the failures of proving something with fold and fold are captured by these models of weak separation logic? In other words, is fold and fold complete for weak separation logic? Then I'm going to talk a little bit about the practicality of those rogue models and then conclude. So what is WSL, weak separation logic? So it's a logic, it's a weaker semantics that relaxes key requirements of separation logic with inductive definitions that are incomplete. So in weak separation logic, heaps are allowed to be infinite and not just finite. In weak separation logic, interpretations of inductive definitions are allowed to be any fixed point and not just least fixed points. And also, we relax the semantics of background theories in weak separation logic, and you can see the details in the paper, but for this talk, I'm going to ignore background theories. And all of these relaxations mean that weak separation logic has strictly more models than separation logic. And we have this theorem that fold and fold reasoning is sound for weak separation logic. So when we reason with fold and fold, we must consider all the models of weak separation logic. And to really reiterate and drive this point home, so when we look at an entailment, we have this world of models of separation logic that we think of. But actually, when we use fold and fold, there's this larger world of WSL models. And we have these models in the difference, these rogue models. And when there's rogue counter models, so rogue models that violate the entailment, this will lead to failures of fold and fold reasoning. Okay, so let's see this in practice, going back to this entailment that we were not able to prove. And we can look at the rogue counter model for it. So it looks like this. We have an infinite heap, where we have the heap locations A, C, B, nil, but also these infinite heap locations 0, 1, and so on, that are where A points to 0, points to 1, and so on. And in this rogue counter model, we have this LSEG relation between A and C. So LSEG AC is true. And this is justified because LSEG 0C is true. And that is justified because LSEG 1C is true, and so on and so forth. And you can see this is not a least fixed point interpretation, but it is a valid fixed point. And conversely, we have none of these relations. So there's no LSEG AB, no LSEG 0B, and so on. And this is also fine, right? These relations won't exist in a least fixed point, so they don't have to exist in any fixed point, right? It's not the greatest fixed point, it's just some fixed point. And you can see that this model satisfies the antecedent of the entailment, but does not satisfy the consequent of the entailment. Great. And this model is an actionable explanation of the proof failure. So why is it an explanation? Well, if you believe that fold and fold must take into consideration weak separation logic models, and if you agree that this is a valid weak separation logic model, then obviously this model violates the entailment, and thus the entailment is not true for the kind of reasoning that fold and fold does. And why is it actionable? Well, maybe looking at this model helps you understand that there's something funky going on with LSEG AC, and maybe we need induction there, right? There's infinitely many elements that are in relation, LSEG relation with C, so maybe induction would help. So hopefully I've convinced you this model is useful. So we have two questions. So one, how can we find it, and find it automatically maybe? And second, does this characterize all proof failures of fold and fold, and so must it exist when we have a proof failure? So the first step we took towards finding these models is moving the problem over to first order logic. So first order logic is where I feel at home, so I wanted to move the problem there. And we have this model preserving translation between entailments in weak separation logic and sets of formulas in first order logic. And we have this theorem that there exists a model preserving translation from weak separation logic entailments to formulas in first order logic for some fragment that we call the effectively determined heap fragment of weak separation logic. But this fragment it's a large fragment. It contains inductive definitions, background theories, and it also allows some quantification in the entailments themselves. And from all of the real-world examples that we looked at fell into this fragment. So it generalizes existing and similar encodings that were more ad hoc, but it's like a general formal translation between weak separation logic and first order logic. Okay, so once we are on the first order logic side, we can use the existing tools and techniques of first order logic, and specifically the formalism of symbolic structures to represent and find those rogue models. So looking again at the model that we had before, it can be compactly represented using this symbolic structure, where all of the infinitely many heap locations between A and C are represented with this one summary node in the middle. And I'm not gonna go too much into what is a summary node, but basically it represents all of this. It's just a representation of the exact same model that we had before. And again, the summary node here, which is infinite, gives you a good hint that maybe something weird is going on and you need induction around that summary node. Okay. So this was how to find them. Now, do rogue models of WSL capture all fold-and-fold proof failures? And the answer is yes. So we have the theorem that fold-and-fold reasoning is complete for the quantifier-free, theory-free fragment of weak separation logic. And we have this nice proof, but notice that entailments are quantifier-free, but we still have quantifiers in the inductive definitions. And we have this nice proof where we show this through a series of equivalences. So an entailment with inductive definitions is valid in weak separation logic if and only if some set of formulas is unsatisfiable in first-order logic. And this is exactly our model-preserving translation. Then, using tools of first-order logic, like Herbrand theorem and compactness, we know that a set of formulas is unsatisfiable if and only if a finite set of ground formulas is unsatisfiable. And then we have this lemma that identifies a finite set of ground formulas in first-order logic with a finite set of fold-and-fold proof steps. And the result of this loop is that we can conclude that indeed entailments with inductive definitions are valid in weak separation logic if and only if there exists a finite proof with fold-and-fold reasoning, which means that fold-and-fold is complete. Great. So this means that all proof failures of fold-and-fold are due to the existence of rogue WSL countermodels. So there's an equivalence between the two. And basically, this fragment of quantifier-free, theory-free is the best we could hope for when we think just of fold-and-fold reasoning, because fold-and-fold by itself can't do any background theory reasoning and can't do any instantiations of quantifiers in the entailments that are not in the inductive definitions. Okay, and beyond the completeness result of fold-and-fold, actually, the translation that we introduced works for the entire EDH fragment, which goes beyond theory-free and quantifier-free. And this gives a complete proof mechanisms for the entire EDH fragment that goes by translating to first-order logic and then using a complete proof system for first-order logic. So the effectively determined heap fragment admits a complete proof mechanism. Okay. So we took these ideas and we implemented them in a prototype tool where we take entailments in weak separation logic or in separation logic. Syntactically, these are the same. And we translate them into first-order logic. And then we apply our symbolic model finder to try and find counter models to these entailments. And we ran the tool over the SLS benchmark, which is a benchmark of entailments in separation logic with inductive definitions. It has over 700 examples divided into several parts. And for one of the parts, we found rogue counter models for 92% of the examples. So some parts have actually entailments that are valid also in weak separation logic, and in those cases we can't find rogue models. Other parts use a lot of background theories, but for one of the parts, which is mostly just inductive definitions, we found 92% for the example counter models. Okay. So to conclude, I talked about how fold-and-fold does not capture the precise semantics of separation logic with inductive definitions. I introduced weak separation logic, which gives weaker semantics to separation logic with inductive definitions, which talked about how fold-and-fold is sound and complete for weak separation logic. So basically, that logic is the logic of that reasoning mechanism. I talked about how the larger EDH fragment is also complete. And the heart of these results is this model-preserving translation from weak separation logic to first-order logic. Also, I talked about how this can be used in practice to see why specific entailments are not provable. And we have a tool to automatically find these counter models. And that's it. Thank you.
Hi. Hi, thanks for the interesting talk. So I was wondering, in the example that you show, you could basically do it with induction, and then the two things that you remove in weak separation logic are the two sources that would give you an induction principle, right? The finiteness of heaps and then the least fixed point interpretation. So if you add basically an induction principle, would you recover the completeness, or do you think it would still be incomplete but for some other reason?
Yeah. So it would still be incomplete. There's no like one induction principle that we can do or a schema of induction principles that would work for everything, and it stays incomplete. So even with these principles, there's no complete proof system for separation logic with inductive definitions.
So would you have an example?
Not at the top of my head.
Oh, we can take it offline maybe.
Just a quick follow-up from that. I mean, it seems a bit strange to me that you have a system in which you have inductive definitions, but no induction principle for reasoning about them. I mean, shouldn't they go together?
So usually in separation logic, when you work with inductive definitions, you do have like actual tools use inductive rules, but they're not complete. They still don't give you a complete proof system. And we wanted to focus on like the basis of these tools, which is the fold and fold, which has no sense of induction. And maybe this explains why in weak separation logic we have any fixed point and not just least fixed point.
Hi. So you said that in 8% of your examples you cannot produce a counter model. Is it because your tool can diverge, or is it because it always terminates but it can't take very long?
So some examples might be valid in weak separation logic, and in which case our tool sometimes is able to say this is valid in weak separation logic, but sometimes even when it's valid, it can't because it's not tuned to that. The other thing is that there's not always a symbolic model that represents a row counter model. So you can't find all models that exist, and in that case, the tool, like you said, diverges.